This will be the final class for the second part electromagnetics. Okay, so this week, I think this Saturday you will have quiz 2, right? So that some student ask me whether I have some more sample questions for you. Okay, this is very important. So that, for me, I actually prepare a lot of sample questions for quiz 2. For quiz 2, so that I have already sent the question. Okay, send the question to our own tutorial class course site. So that you log into this one. So remember, it's our own tutorial class. Then if you go to this, you click content. There will be 罗语 part of summary lecture, because in the past I am responsible for the summary lecture, and somehow some other young faculty lead the class, so that I give them to them. But I still have a lot of sample questions there, so that you look at week 5 to week 7. So each of this each week here I give 6 to 10 more quiz questions for you to attend. Okay, so if you want to rehearse, remember, okay, there are more sample questions just in our own tutorial course time. Okay, you can take a look. Any question? Okay, good. If no question, maybe then I will start our class today. Okay, so student online, can you see my slides? I share here. Can you see my slides? Student online. Yeah. Oh, okay, good. So that's, as I said, today will be our last class on electromagnetics. From next week, we are going to start. We are going to study quantum physics. So quantum physics, we have a lot of new concepts there. Okay, we have a lot of new concepts there. So then it's very, very important. In the past, I don't require you, for example, to go through for example, the LAMS video or the summary lecture. But now, when quantum physics start, I think everyone of you need, to watch the LAMS video and also attend the summary lecture, because we only have 1.5 hours for the tutorial, so that I need to go through the the content and quantum physics very, very quickly, so that we will have enough time to go through the tutorial, so that I cannot talk in detail content like what I do for optics and electromagnetics. And also quantum physics, I would say, is very abstract. So it's very important for you to first get familiar with what such concept is. And then before we are going to tutorial question. Okay, so today, I'm going to cover 3 chapters. Okay, chapter 7 to chapter 9. So first of all, Faraday's law, then inductance and Faraday electromagnetic wave. So among these 3 chapters, Faraday's law is the most important one. So this is why I will spend about 1 hour on Faraday's law, and only half an hour on chapter 8 and chapter 9. Because chapter 8 and chapter 9, I think the concept is minor, so that we can so you can see the question is normally quite easy. So first, before I start chapter 7, so there are 2 questions, okay, about the magnetic force and the magnetic source. Okay, actually, this is related with what we have learned last week, but the tutorial question, is left here, so that let me first go through this, another 2 tutorial questions about magnetic force and the magnetic source. This can help you to, for example, to rehearse what we have learned last week. So first, let's look at tutorial question 1. Okay, tutorial question 1. So what this question tells us is, here we have 2 wires. Each have a mass per unit length 40 grams per meter. Okay, so you don't lose the length, but it tells you the mass per unit length. Okay, for this 2 wires. Okay, they are supported in the horizontal plane, which means both of them are on the same horizontal plane, and then by a string 6 centimeters long. So which means each string here is 6 centimeters. Then each wire carries the same current I. Okay, So when the wire carry a current I, so that it will just generate magnetic field, right? Then magnetic field generated by one wire will exert a magnetic force on the other wire. Okay, cause them either to repel or attract each other. Okay, what this question tells us that because of the current supported in the wire, these two wires will repel each other such that the angle between the supported string here, theta, is 16 degrees. 16 degrees. So that's the question wants us to first determine whether this current is flowing in the same or opposite direction. Then want us to determine the magnitude of this current I. Clear what this question asks for? So first ask us the direction of the current supported in the two wires. Okay, then the magnitude of the current. So clearly, this actually is a combination. This kind of question is very important. In the final examination, maybe it will have some chance to be tested, because it not only tells us, for example, this FID rectangle rule for magnetic force. It also tells us magnetic source, how a current will generate magnetic field. So it's a combination of these two. So contest humanly concept. So that first we should understand why there will be a magnetic force between these two wires. So as I said, this is because one wire, support a current. We know from last week, a current driving wire will generate a magnetic field. According to Ampere's law. Once a magnetic field, exists in the space, and then FB equal to IL cross B will also generate a magnetic force, right? So what this question wants us to know is, for example, I suppose wire 1 has a current, flowing to the top. Then it will generate a magnetic field at wire 2. Then it wants us to determine whether the current supporting wire 2 is flowing in the same or opposite direction, such that the magnetic force here will be repelled, will be a repulsive force. So first, what we should understand here is, we assume, for example, wire 1 has a current flowing to the top. Then we determine whether wire 2 should have a current flowing to the top or to the bottom, so that we will get a repel force, repulsive force. So first, if wire 1 here is a point to the top, can you let me know, in this case, the direction of the magnetic field at wire 2 is along which direction? So, for magnetic, so clearly this is for magnetic source. Okay? So for magnetic source, if I have a current, let me help you first to, for example, review what we have learned last week. 3 right-hand rules. So first right-hand rules is FB equal to QV cross B. Okay, moving charge will experience some magnetic force. Second is FIB. Okay, FB equal to IL cross B. Line driving current will experience some magnetic force. The last one is a current will generate a magnetic field. Right-hand rule in this way. So force is using 3 fingers. Okay, 3 fingers are 2 right-hand rules. For magnetic source, only 1 right-hand rule is this one. Or thumb always point to the direction of current flow. 4 fingers enclose the direction of magnetic field. So in this case, as I said, wire 1 is flowing to the top. We apply our right hand in this way, so that it will give us a magnetic field at wire 2, point into the page, right? Then can you tell me, if my wire is flowing, for example, wire 2, the current is flowing to the bottom, where will be the direction of the magnetic field? In this case, now I have B here pointing into the page. If wire 2 is flowing to the bottom, the magnetic field, magnetic force will point to the right or point to the left. IL cross B the magnetic force is 3 finger. Any idea? Very good. It's point right. How should we do this? I is here. B pointing into the page with our thumb point to the right. Okay. So which means in this case, current Y1 will repel current 2, right? Because the force is on the right. So on the other hand, if my Y1 will have a current, flowing to the top, so the same as Y1, this is how we should apply our right hand. Okay, student and team. Okay, look at my finger. So this is how we should apply our right hand. I, B, and then my force on the left, this will be attracting force. Okay? I, B, F. So which means in this case, because the question tells us the two wires repel each other, so that wire 2 should have a current in the opposite direction with respect to our wire 1. Okay, so we have already determined here they should have a current flow in opposite direction. Okay, then this gives us an important conclusion. Okay, important conclusion. If we have two current driving wire, if the wire are the two current flowing in the same direction, these two wires will attract each other. If they flow in opposite direction, they will repel each other. Okay, so this question actually sometimes will be tested in the final examination. So that if it asks you, okay, how to use your right hand to determine the force between two wires, this is what you should do. Okay, so first remember, on the same direction attract, different direction repel for wire. Then what we should do is first apply our right hand rules for magnetic field, magnetic source generate magnetic field, and then IL cross B. Okay. Then these two wires, when they have current on different directions, so that they will repel each other. Then if you analyze the force experienced by each wire, so you will find, okay, how many forces each wire experience? How many? 2 or 3? 2 or 3 force each wire experience? Only 2? What are the 3? Very good. So actually it generates, so it will experience magnetic force Fb, okay, repel, tension force T, and gravity mg, right? So that if we analyze the force, on the vertical direction, then my tension force times this theta. Okay, this theta is just 1/2 of this 16 degree, 1/2 of this degree, so theta equal to 8 degree. Okay, so which means my T times cosine 8 degree equal to the gravity mg, because it has to cancel out the gravity. So on the horizontal direction, this tension force has to cancel out the magnetic force. So T times sine theta, which is sine 8 degree, should be equal to my Fb. So that if I want to cancel out my tension force, this equation divided by this one, my Fb divided by mg equal to sine theta divided by cosine theta equal to tangent 8 degree. Okay, tangent 8 degree. Now m is given, actually m is just equal to the 9 mass density times the length L. Okay, then let's look at how to get Fb. So Fb, of course, equal to this IL cross B. So I is given, L, so is a length. So we will talk about how to deal with this part later. But then we also need to calculate what is my B. What is my magnetic field B? So this can be done by what law? Magnetic field equal to how much? B equal to, according to Ampere's law, a single wire mu naught I divided by 2 pi r, right? This is the Ampere's law we learned last week. B equal to mu naught I divided by 2 pi r. So the question only tells us the length of, for example, the string. Does not tell us the distance between these two. Does not tell us the distance between these two. But clearly the distance between these two is just twice of this L times sine 8 degree, right? So R just equal to twice this L which is 6 centimeters times sine 80 degree. Because if you look at this right angle, okay, this length times sine 80 degree equal to this guy. This is just 1/2 of the distance between these two wires, so which is r. So we can write 2 pi r as 4 pi times r divided by 2. As I said, r divided by 2 is this guy, which is just, this length times sine theta. Okay, this length times sine theta. Then both I naught, so I naught is what we want to determine. Then once you substitute I into this equation, as you can say, my FB equal to ILB, right? So here we have an L here. So then what is mg? Mg is actually, so G of course is the gravitational constant. Then M is the mass. Mass equal to the 9 charge density 0.04 given in the question times the length L, right? Because the question tells us how much mass per unit length. So although L here is not given, but you can say FB and both FB and mg are proportional to L, so that this L cancel out each other. This L cancel out each other. So that within this equation, okay, within this equation, I naught is the only unknown parameter. Okay, I naught is the only unknown parameter if you cancel out SG here. So you can say, then when you rearrange this equation, you can get the I naught just equal to square root this guy. You can say G is given, 80 degrees is also given. Mu naught is what you can find in the formula sheet, so that you can show I naught is actually 67.8 ampere. Okay, any question? Any question? Okay, so if no question, now let's consider another one. Okay, so this is a question tested about 1.5 years ago. Okay, so here we have two long cables A and B. They are aligned parallel to each other and separated by a distance 0.5 in meter. 0.5 in meter. So cable 1 carries the current I equal to 20, while cable B carries a current I equal to 50. They are flowing on the same direction. Flowing on the same direction, again, this should be attractive or repulsive force. Hello, I already told you, current flowing on the same direction, this should be attractive or repulsive force. Very good, it should be attractive. So I will show you later why. Then the first one is I want you to determine, okay, of course, A and B should be attractive or repulsive force. And then find the magnitude of magnetic force per unit length acting on cable A and B. So this is what we should do. So let's say why is attractive force. Okay. So the current are flowing on the same direction. So that way, for example, assume they are both flowing to the top. Apply or right hand. In this way, cable A will generate a magnetic field at the position of cable B into the page. Okay, this should be into the page. Okay, then IL plus B. Again, IL plus B. I, B, FB. Okay, I, B, FB. Index finger point to the top, current flow. Middle finger point into the page. B point to the left. So this is clearly an attractive force. Okay, this is clearly an attractive force. Then, according to IL cross B, of course, the F is on the left, so that is an attractive force. So that when we want to determine the magnitude, what we should do first, of course, is to determine what my B it is. Okay, what my B it is. So B here is mu naught I divided by 2 pi r. So the question already tells us, the distance between these two wires is 0.5 meter. IA is 20, IB is 50. So that we put IB here, we can get my B is about 8 micron Tesla. 8 micron Tesla. Okay. Once B is given, as I said, F equal to IL cross B, IL cross B. So that because I and B are perpendicular to each other. So that, yes, any question? Any question? Okay, so that my final force should be IBL times so I times L times V. The question wants us to determine the force per unit length, which means L is equal to 1 meter, okay? Because it's force per unit length. So you just set L equal to 1. B is we already calculated, I is given in the question. So that we get the final answer is just 50 times my 8 micron Tesla, so which is 4 times 10 to the minus 4 Newton per meter, okay? 4 times 10 to the minus 4 Newton per meter, okay? Any question? So if no, let's look at Faraday's law. So first, what Faraday's law it is? Okay? Faraday's law tells us that, okay, if we have a closed circuit, we put a closed circuit in the magnetic field. Okay, because it's closed, there will be a certain magnetic flux will penetrate through my circuit, right? Then, important, if somehow this flux is changing with time, then there will be a voltage generated within this loop, and this voltage will generate an induced current. This is what Faraday's law tells us. Okay, so in more detail, Faraday's law states that voltage in a closed circuit will be generated, and its magnitude is directly proportional to time rate change of the magnetic flux. Okay, time rate change of the magnetic flux. Okay, so mathematically the voltage epsilon. So the voltage is what we call the EMF. My EMF equal to minus d phi b divided by dt. Okay, I will talk about this minus on later. Okay, this minus on gives to Lenz's law. But if we just look at the magnitude just equal to the magnitude d phi b divided by dt, time rate change of the flux. Then look at this equation. Can you tell me how many ways can I get an EMF? If I want to get my EMF, I need my magnetic flux to changing with time. If I need my phi b changing with time, what can I change? BA or any other things in order to make my phi b changing with time? Yes, very good. Actually, there should be 3 ways. Normally, you can directly say we can change the magnitude B. Okay, if the magnetic field itself is changing with time, of course, phi b will change with time. And also, if my area, I make my, for example, circuit larger or smaller, for example, like a string, we can also make the flux changing with time. We can create an EMF. Most important thing is here we should, you know, this is B dot dA, the inner product between the magnetic field and the surface area vector. So that, you know, the magnitude is actually has a theta, okay, cosine theta. You can also locate our circuit so that you locate the angle between the surface and the magnetic field. In this way, you will also be able to make the magnetic flux to change, okay? So, you know, actually, this is actually an ordinary ways people use to generate the AC currents, okay? Tesla use this way to generate the AC current. We have a very large circuit loop, then rotating in a uniform magnetic field. So that because this theta is changing, so that we can get you know, AC voltage out of this procedure. Okay, we should have actually 3 ways. The 4th way is actually given in the lecture notes that I copy, but it's a trivial way. Any combination of the first 3, of course. But normally, if the final question examination asks how many ways we can get an AC, for example, we can get an EMF. For example, the final examination. So I think you should also, if you want to get a full mark, you comment the 3, right? We can either make the magnetic field changing with time, make the area changing with time, larger or smaller, or make my circular loop to rotate so that I change cosine theta. 3 ways. Okay. So there are another 4th way. Okay, a 4th way. The current, if I have the n turns of the loop, and then my EMF is actually, you should put n turns here. So which means changing the term, we will also be able to make the EMF larger. Okay. Now, this is an experiment. This is an experiment. So show you how we can really generate an voltage, across this procedure. So in this experiment here, the professor from this Purdue University, they just use, they just test the EMF generated in this 3 wire. So this one is just one term, 10 term, 100 term. So you can take a look how this number of n will affect the magnitude of my voltage. And also, if I make my magnetic field to change very faster, it will also get a larger voltage. Okay, so this is an experiment I would like every one of you to see. Right, we make the voice larger. Okay, so let's look at this video. Why it's very serious. Yeah. Sorry? You need to connect to the audio here, not the. So how can I connect to audio? The audio is connected right here. I think it's automatically connected. Why is the audio not here? Sorry. Why it's not here? So it's from here, not from the. Let me see. Try to sound it off and on. Here? This is the single ear. On top of the speaker and the phone down. Where? This one? Just open the. Oh, I hear this brings the rest. This one? This one? This one? This one. Okay, let's see whether this works. Okay. No. No voice. No voice.
Well, I tried offing it on
Okay. One.
I off and on again because sometimes it resets everything else.
Okay. Are you sure?
Yeah, I did. Takes a while. Sometimes a bit buggy, right? This system.
But if it doesn't work, maybe I will just experiment myself.
Taking a while.
Yeah, so we wait for 1 more minute, okay?
Just stand there. Why is it taking so long to off?
Normally you have to wait for 1 minute. It's okay. We should have enough time. So sometimes there is some problem with the audio connection. Okay. I think you can start very fast. So let's say it again. Voice. Sorry?
Put your amplifier close to the speaker.
No, there is no amplifier. Maybe anyway, I will just have this. So as I said, what this video want us to see.
Yes, you can put your thing there.
Which thing there?
Your speaker.
This speaker. No. It's that will be very inconvenient. So anyway, so what, as I said, what this question, this video want us to look at is how the term of each circuit will affect the voltage. Okay. So first, let's look at the experiment done by here. I have just one terms. You can say this is an amperemeter. Okay. If I make a magnetic field, magnet actually put it through this wire. Okay. Because a magnet is moving. This is a magnet. Okay. This is a magnet. If this magnet is moving, it will make the magnetic field penetrate through this single wire to change. So you can say, because the magnetic field change, it will cause this amperemeter, to shift. So because it's one wire, it only has a very slight shift, which you cannot see. But if we connect it to 10 turns, so which means we can make the voltage to be increased by 10 times, then you will see the voltage will become much larger. The current will become much larger, right? You can say, right? Moving in to move to the right, moving out, it will move to the left. You can say you move slowly because my phi is changing very slowly, so that's the force. But if I move faster, let's look at it again. If you move faster, the amperemeter will move more, so which means the voltage is larger. If you move very slowly, and then the amperemeter will move just very a little, which means the voltage is small. See, so very slowly, so and then there nearly low voltage, but faster we will get more large voltage. Now let's look at what will happen for this 100 turns. Okay, you can say even very slow movement, it will move the voltmeter to move very fast. This is because N is larger. We increase it by 100 times. Okay, of course, if you move it very faster, you can get very fast. You can get a very large voltage. Okay, so actually this is the experiment that show you how N and also how fast the phi changing will give us a non-zero voltage in the circuit. Okay. So now you already understand that my voltage here is proportional to both the term as well as the time rate change of the flux. Now you may wondering what will be how to determine the direction of the induced current or the induced voltage. So that's right. Because when you have changing flux, it will cause a current. The current can either flow clockwise or counterclockwise. How to determine whether the current should flow in the counterclockwise or clockwise direction? This will be given by the Lenz's law. So first, let me read what Lenz's law is about. It states that the polarity of the induced voltage is always in a direction such that it will tend to produce a current that will try to create an induced magnetic flux to oppose the change in the source magnetic flux. Okay, or there are actually some keywords. The induced current, okay, you know, the induced current is different from, for example, the source magnetic field, okay. The induced current will try to create an induced flux that try to maintain the original flux. Okay, so it looks very complex. Okay, But here I just want you to summarize. So how to judge the flow of the induced current? Okay, so we have two situations. So first, you know, we have a source magnetic field. This source magnetic field, if it's changing its power, it will create an induced magnetic field, okay? It will create a current. And this current will give rise to another induced magnetic field. Then whether this induced magnetic field should along the same and a different direction, depending on whether my source flux is increasing or decreasing, okay? So for example, if my source flux is increasing, then in this case, my induced flux due to this induced current should be on the opposite direction of the source field. Again, if my source field is increasing or my source flux is increasing, either because of the increased magnetic field or increased area, okay? But as long as my source flux is increasing, my induced magnetic flux, my induced magnetic field should always along the different direction, opposite direction of the source field. But on the other hand, if my source flux is decreasing, either because of the decreasing D or decreasing area, then my induced flux due to this induced current should be along the same direction as the source field. So let's look at the left-hand side, for example. If I assume my source flux is increasing, then, as I said, the induced current should always try to create a field to oppose the change, so that this induced magnetic field should along opposite direction. So that we should apply or write in this way, right? Because my field should now point to the bottom to opposite the source field, then it should flow, the current should flow in this clockwise direction. But if the source flux here is decreasing, and then my induced field should along the same direction of the source field, we should apply or write in this way, so that it should flow in the counterclockwise direction. Clear? Any question? So if no question, let's look at two tutorial questions to help you strengthen your concept. So here I have a circular loop with 5 turns and a radius of 15 centimeters. A magnetic field is aligned perpendicular to the plane of this wire. It changes linearly from positive 0.8 Tesla to minus 0.4 Tesla in 200 milliseconds. Okay, so clearly the source field is decreasing. If the source field is decreasing, causing the flux to decrease, and then the induced field should along the same or opposite direction to the source field. It should along the same or different. The same, right? Because it's decreasing field, as I said. So note that the question tells us the positive magnetic field refers to the field point away from us, while the negative magnetic field refers to the point towards us. First, I want you to calculate the induced EMF in the circular loop, and then determine whether the induced current should flow in the opposite or or should flow in the clockwise or counterclockwise direction when as we see, okay. So first, the magnitude given by the Faraday's law, m times d phi dt. So phi equal to b times a because it's perpendicular, okay? Phi equal to b times a, directly b times a. So that a is unchanged. So that we just put a out of the differentiation. So n is 5. A is a circle with a radius 0.15 meter. So pi r squared is a. Then what is dB over dt? dB over dt is the time changing rate of the field. So the question tells us that it changes from 0.8 to minus 0.4 in 200 milliseconds. So that we use the initial field minus the final field divided by the time rate, okay? So that we can directly get what my epsilon, my voltage it is, 2.12 volts, okay? 2.12 volts. Any question? So if no question, now the second part want us to determine whether it's clockwise or counterclockwise. So clearly the source field initially positive direction is point away from us. It's decreasing. So which means that induced field should be around the source field, right? If the induced field around the source field, which means my star should point away from me. Then if my star point away from me according to my right hand, so my forefinger should flow in the clockwise direction. Okay? Should flow in the clockwise direction. So that we should say the corresponding induced current should flow in the clockwise direction. This is because the induced field should be around the standard direction of the source field, point away from us. But if the source field is increasing, then this is how we should apply our right hand, because the induced field should be on the opposite direction of the source field. So that our thumb should point into me. Okay, so that we will get a counterclockwise current flow. We should get a counterclockwise current flow. But here is increasing from a positive to a negative value. So this is what we should apply our right hand. So we should get a clockwise current flow. Okay, this is how you should comment here. Any question? Good. No question. Let's look at. Okay, so this is actually a question tested 4 years ago, but I don't think I have time to talk about it in more detail. But solution is provided here, so that you do yourself after the class. Okay, you do yourself after the class. Okay. So the motional EMF. Okay, so this is actually a very important concept, which is very so quite often tested in the final examination. So Faraday's law tells us if I have a closed loop, if we have a closed loop, so that we will get an EMF. But actually, if you don't have a closed loop, if you just have a single wire is not a closed one, right? If you move this single wire in a magnetic field, you will also be able to get an EMF, a voltage across its two ends. So which means a moving wire in a magnetic field can serve as a voltage source. It can serve as a voltage source. And the voltage difference between the two ends is given by BLV. B is a magnetic field, L is a mass, V is a velocity. Sorry? L is the length. Yeah, L is the length of this wire. The longer the wire is, the larger the voltage it is. Faster you move, you will also get a larger voltage. Okay, of course, larger magnetic field gives us larger voltage. Then this is a very important one. You have to keep in mind. There will be the fourth right-hand rules or the only right-hand rules for today's class. You may wonder which end will have higher potential, or how the current will flow in this voltage in this wire. Okay. Then this is what we should apply our last right-hand rules. Okay. V cross B. V cross B. V, B, or thumb will point to the current flow within this wire. Okay. Or it will point, with a voltage source. The current flow direction is where the high potential ends appear. Okay. So you apply V cross B, for example, in this case, V is on the left, right, B is pointing into the page, my thumb points to the top. This is show us how the current will flow within the wire. So negative electron, flow to the bottom, positive charge flow to the top. So we will have a current flowing to the top. And also the top side will have high potential. Okay. So within that voltage, the current flowing direction is where the high potential appear. Okay, where the high potential appear. So this is what you should bear in mind. Or last rectangle goes V cross V gave us a current flow in a moving wire. And also the direction of current flow is where the high potential appear. Okay? So this is very important. Then with this, I would like to use, actually I have delivered this question on learning catalytics, okay, with this session number. You can take a look. So I will give you 3 minutes to submit your answer. So here I have an arrangement given below. So where I have a rod lying a U-shaped conductor, of course making good electric contact. I said the arrangement is placed in a magnetic field into the page. If the magnetic field is strength, whether the rod should move to the left or move to the right. Move to the left or move to the right. Okay. Yes. Oh, sorry. I don't think I have delivered. Okay, I give you 3 minutes to submit your answer. Okay, take a look. So first, the magnetic field is decreasing. Then you should try to look at whether the induced magnetic field should point into the page or out of the page. Induced field should be into the page or out of the page. Yes, very good, because it's decreasing, so that the induced field should have the same direction. It should point into the page. It should point into the page in this way. So if it's pointed into the page, which means my current should flow in this clockwise direction. If my current is flowing in this clockwise direction, and then across IL plus V to get the field. Apply IL plus V to get the field. What will be the direction of the force? B equal to IL plus B. FB equal to IL plus B. What will be the direction of the force? Yes, very good. It should to the right. So that why is because now I already get the current flow across F equal to IL plus B. Okay, F, IB. I to the bottom, B is into the page. I should get a force to the right. Okay. Or another thing is actually we can also apply the Faraday's law. Faraday's law tells us okay, if the source, if the field is increasing, actually this wire should move in such a way that try to maintain the flux. If the field is decreasing, should my area be larger or smaller in order to maintain the flux? Yes, very good. My area will become larger in order to supplement or in order to compensate the decreasing field. Okay, only when my wire move to the right, it will make the area larger so that the flux will be more or less unchanged. Okay, so both approach points that the slide should move to the right. Okay, my wire should slide to the right. Okay, we should choose B. And let's look at question 2. Okay, we have to move faster. So here we have a rectangular loop with resistance R, okay? With our resistance R, total resistance is R, and then it has n turns. So that NBIL is my voltage. Each of the each of my so each a loop has a length L and a width W. This is L, this is W. Then it moves into a uniform magnetic field with a velocity V. I want you to comment what is the magnitude and the direction of the resultant force on the loop in the following three conditions. First, enter. Second, move in the field, and then finally leave the field. So now let's look at this question one by one. So when the loop is moved in the magnetic field, you can say this H, D, and AC, they are both out of the magnetic field. Only this wire is moving in the field. So actually, we can solve this question using this motional EMF, okay, motional EMF. So we have n turns, so which means I have n number of H is actually moving in the field. N times B, now my L should be the weight W, okay? BW, V is dx divided by dt. NBW, okay, is my voltage. Or you can also apply Faraday's law, N times d phi over dt. So that's what is my phi? Phi is B, okay? This B times the area here, this area here. So this is W, this is X. Okay, because B and W are constant, the movement out of the bracket, so that it will also become NBW times dx divided by dt, which is V. But if you directly apply motional EMF, you will get the answer much faster, because NBW, BW is just the motional EMF due to one wire, because we have n turns, so that we will on this side. Okay, you can directly use motional EMF. Once I get my voltage equal to NBW, then my I is equal to epsilon divided by the resistance R, Okay, once I is given, I can use F equal to NIL cross B to get the magnitude. Okay, so you just times this guy I by N and L. Okay, by N and L. Okay, so if you times I by N and L, this is what the sorry. If you times I by L and B, so L here is my W, B here is my magnetic field, so that you should get this guy. Then what should be the direction? As I said, first we need to determine the current flow in this wire. As I said, the current flow in a motional EMF is given by V cross B. Right? V cross B. V always point to the left, B point into the page. My thumb should point to the top. So that which means in my current I, B, the current is actually flowing to the top. Right? V cross B. Once I get the current flow, I apply F equal to BIL. Then my second right-hand rule from last week. F equal to IL plus B, which means FIB, I to the top, B into the page. Now my F is to the left, so that I get my FB here is to the left. Okay. Any question? Okay. No question. Let's consider. Okay. Part B. When the loop exactly move within the magnetic field, what will happen? When my loop exactly move in the magnetic, what will happen? So of course here will be low voltage created. Yes, any question? Hello? Okay, good. So that when my loop exactly move within the voltage, okay, within the magnetic field, you can say the magnetic flux will remain unchanged. If the flux will be unchanged, there will be low current or low EMF. So what you can also view this as, okay, now both edge, okay, both edge is now within the field, so that they will have the same EMF, they will have the same EMF, and this side will have an EMF to the top, this will also have an EMF to the top, so that's the cancel out each other, give us zero EMF within the whole loop, okay, within the whole loop. So the finally, so what we should do is still do the same, okay? When B is out of the magnetic field, we consider only the EMF created by D. So again, it's another NBWV, okay? NBWV, I can get I, and then you will get an FB in exactly the same form, As I said, now D is served as a motional EMF across V cross B. The magnetic field and the current, on D should also flow to the top. Right? The current should also to the top. Yeah, any question from the student? So the current flow should also to the top, then apply this F equal to IL plus B again, we get the force to the point to the left, okay? You get the force to the point to the left, okay? So any question? So this is the same as the first one, just the force. The first thing is the force acting on B. Now this force will acting on A or on B. But the current flow, will be on different direction, okay? Because when the current is on B, current flowing on B, it will give us a counterclockwise current flow, okay? Counterclockwise current flow. But if the current is flowing on D, it will give us a clockwise current flow, okay? Clockwise current flow. But nevertheless, the force will always acting on the left, okay? Because the current flow on this source will always flow from bottom to the top. It will be unchanged. So that apply FIB on right hand, it should point to the left. So yes, this is a question test last year, 1 year ago. Oh, sorry, 2 years ago. So here we have a metal rod pulled with a constant velocity v along two parallel metal rail connected with a metal strip. Okay, connected with a metal strip. Okay, a uniform magnetic field of 1.5 Tesla is directed now out of the page. Okay, then I tell you the rail are separated by a distance, this L equal to 60 centimeters. Then this wire is pulled at a speed of 45 centimeters per second. I want you to comment on what is the magnitude of the voltage generated within this, within this metal wire. Then, if the metal rod have a resistance 18 ohm, the metal rail and the metal strip have negligible resistance. I want you to determine what is the magnitude and the direction of the current within the loop, okay? Within a loop. Now I want you to determine is clockwise or counterclockwise. And finally determine how much is the mechanical power required to pull this wire at the speed of 45 centimeters per second. So let's look at 1, 2, 3, one by one. So first, magnitude of the EMF, of course, this is motional EMF, BLV, right? As I say, it's BLV. B is given, L is given, V is given. So directly substitute all the, once you realize this is motional EMF, directly submit, substitute, all the parameters into this equation, you can get the answer is 0.405 volts. Okay, this tells you to directly, apply this motional EMF. You should realize actually, if I pull a wire on a strip, this is always motional EMF. Okay, this is always motion EMF because this wire is moving at a speed of v. This wire is moving at a speed of v. So BLV is the voltage. BLV is the voltage. BL and V are both given in the question, so that we can get the voltage. Then the current is applied the Ohm's law, sigma divided epsilon divided by R. We can get the current. Okay. So this is directly apply the formula. Then what we should look at is whether the current should flow clockwise or counterclockwise. Then can you tell me, apply all force right-hand rules, the current flow in the rod should along which direction? V cross B. Yes, to the top. Very good. So this is how we should apply the right-hand V, B. So current flow in the wire should to the top. If the current flow in the wire is top, then I should get clockwise or counterclockwise current flow. Because the question wants us to determine in this loop the current should flow in clockwise or counterclockwise direction. Clockwise, right? Because I is flowing from top to the bottom. So that it flow in this direction. In order that on this yellow rod, it should flow top to the bottom to the top. Okay, from bottom to the top. Okay, and then we should get a clockwise current flow. Clockwise current flow. This is what you should comment here. The induced current should flow in the clockwise direction. In the clockwise direction. Okay. Okay. So another way to look at this is when the slight shift to the left, so which means the area of the loop is become larger or smaller. Area become larger, which means flux is increasing. If flux is increasing, the induced current, the induced magnetic field should along opposite direction of the source field, right? So that our thumb point in the page, apply the Lenz's law, I get a clockwise current flow. A clockwise current flow. So this is the other way to look at this problem. Of course, but I think BLV apply motional EMF will be much easier. Directly, BLV give the current flow. The current flow from bottom to the top, of course, it give us a clockwise current flow. Okay. So that finally, I want you to calculate the total power in order to move this at a constant speed, so that it should give the total electric power generated by this circle. So which is Epsilon squared divided by R, Epsilon squared divided by R. So which is about 9.11 micron volt. Okay, yeah, micron volt. So that this is the power, mechanical power required. Okay, mechanical power required in order to generate, such electric power. Okay. So the last question on this part is, okay, here I have a conducting rod of length L, move with a constant velocity parallel to a long wire with a steady current I. The axis of this rod is maintained perpendicular to the wire with the rear end at a distance R away from this wire. I want you to show that the voltage induced in this wire is given by this equation. Okay, so now let's rephrase this question. This question says first we have a source current. This source current, according to Ampere's law, will generate a magnetic field in the space. Right? Now I have another wire without any current, but it moves in the magnetic field of this source current. Because it moves in the magnetic field, so that it will have motional EMF. I want you to determine how large is the motional EMF on this moving wire. So this wire is moving parallel to the current flow, while itself is perpendicular to the source current. Okay? So that first we want to apply the motional EMF. So first, also the question wants us to determine which ends will have a higher potential. So in order to determine which ends has a higher potential, what we should do is to look at first the magnetic field at this wire. The magnetic field at this wire should along which direction? According to our right-hand rules, learned last week, into the page. This is how we should apply our right hand. So that the magnetic field is into the page. Then which end has higher potential is given by V cross B. Yes, we'll go to the left side. V, B, point to the left. So that the left side should have higher potential. Okay, so we can quickly determine that. But now that determine the magnitude will be a little bit tricky. Okay, will be a little bit tricky. So BLV, epsilon equal to BLV, that B is a constant. If B is not a constant, what we should do? We have no choice but to do the integration. We divided, okay, the whole structure into infinitely small segments. So for each segment, okay, at a distance x with respect to the wire, it will have a small voltage across to it. Then we integrate or summing up the voltage from the left to the right end, we can get the total EMF. But for each small segment, when we apply BLV, now L is the distance of this segment, which is Ex. So that we get V equal to mu naught I divided by 2 pi x. This is my magnetic field, mu naught I divided by 2 pi x. This is my magnetic field, of course, according to Ampere's law. My L is dx, V is a constant, so that I get the small voltage at each small segment. Then if I want to get the total voltage, I need to summing up each dV, which means I need to do integration from the starting to ending point. Starting point at x equal to r, ending point at r plus L. At r plus L, so which means I put all the constant out of the bracket. So what we have integrated is dx divided by x. dx divided by x is log x. From r to r plus L is just log 1 plus L divided by r. Log 1 divided by L plus r. So this is exactly what the question want us to calculate. Okay? Any question? Clear? Or do you need more time to digest? But look at this question, okay? If you have any question, just let me know after the class. Okay? Any question, let me know after the class. As I said, I don't think the integration question will be tested, very often in the final examination. At least I have never seen that. So that if you find this question is very difficult, so I think it's okay. But what I would suggest you is still, look very closely at our right hand. So I don't think it will test you this examination. So it will test you this mathematics, but it may ask you to determine which end will have a higher potential. BLV is still required. Okay? BLV is still required. Then inductance. So that for inductance, what inductance you have to understand is any solenoid is what we call inductance. So that if you inject a current, through the solenoid, you will also be able to create an EMF. So what you have to bear in mind is in this case, the EMF within this inductor always running from lower, the current, okay, in this inductor always running from the lower to higher potential ends, okay? Current in the inductor always running from lower to higher potential ends. So that if the source current is increasing, so that my induced current should be on the opposite direction of the source current. This is what makes does. Source current increases, induced current should be running on the opposite direction. Okay? Then if my source current is increasing, my induced current running from opposite to it, so that it running from the left to the right ends. As I said, EMF is actually running from low to high potential. Clearly, this one, right end will have high potential. But on the other hand, if my source current, here my source current always enter, from the right, okay? If my source current enter from the right but decreasing, then my induced current should on the same direction of the source current. As I said, it running from low to high potential ends. Now the induced current will leave from the left ends. So this is where I will have high potential. Okay, so this is the law of inductance. You have to judge which side of the inductor will have high potential, which current will have high potential. So that will determine, the induced current leave at which ends. The induced current, the end where the induced current leave the inductor will have high potential. Okay, so this is the case. So another case is about so that is ask you to determine the direction of the EMF. Now the magnitude of the EMF is actually given by the law of inductor. The law of inductor, actually this EMF is proportional to di divided by dt. The time rate change of the source current. The time rate change of the source current will give us the EMF. So that for self-inductors, there are two important laws. So first, the definition of the inductance. So you can view the inductance similar as the capacitance in electricity. So the inductance equal to N phi divided by I. N phi divided by I. N is the number of turns, phi is the magnetic flux divided by I. So this is what we call inductance. Okay, the inductor element, it does not depend on the magnetic field. It only depends on the geometry, similar to the capacitance. This L only is a parameter of the geometry. For example, it is determined by how much turns of the solenoid it is, and then the area of the solenoid. Okay, so this is only a geometry parameter. So once we know the geometry parameter inductance, and then the EMF equal to minus L times EI divided by dt. So the inductance times EI divided by dt give us a voltage. So these are the two important formula of this inductance. One is the definition, L equal to N phi divided by I. The other is L times di over dt, is a voltage. Then before I continue, let's try another example. Okay, another example on the inductance. So first, let me deliver this question on learning catalysis for you to have a try. So now let's look at this question, okay? So it tells us we have a solenoid. Solenoid will only create a magnetic field inside the solenoid, but outside the solenoid, the field is exactly zero. Magnetic field is exactly zero. Okay. Then the question says that if we have another circuit loop, which just circles around the solenoid, so that where at the loop here we don't have any magnetic field. I don't have any magnetic field. Now I make the current in the solenoid increasing, so that the magnetic field inside the solenoid is also increasing, right? The magnetic field inside the solenoid is increasing because by this current around this solenoid. Then I said, what I want you to comment on is the current induced in this loop. If there will be a current induced in this loop, if it is induced in this loop, it should run in the same or opposite direction of the current on this solenoid. So this is what this question wants you to comment. So I give you 1 minute to submit your answer. So at the position of the current, I don't have any magnetic field. But whether there is a magnetic flux through this blue loop, if there is a magnetic flux, you should determine whether this magnetic flux is increasing or decreasing. Therefore, determine the direction of the current flow.
change the
So which one? Which one? Any idea? Very good. Why? First, if the current of this, for example, of this loop, for example, now it's on of this node is increasing, which means my magnetic field inside here is also increasing. If the magnetic field is increasing, which means the magnetic flux through this blue circuit is increasing or decreasing? Yes, is increasing. Flux is decreasing, which means my induced field should along the same or opposite direction of the source field. Yes, very good. It should along the opposite direction. So first, because we still have, flux through this blue loop, okay, is increasing with time. So of course, we should have a current flow. And because the source flux is increasing, so that my induced flux, therefore the induced current should flow along the opposite direction. We should choose B. Okay, we should choose B. Okay. So there will be a question 4, but I think question 4 is go far beyond the final examination. It asks you to determine, okay, how large is the inductance. So I think it will go beyond the class so that I will not talk about how to solve this in detail. But the solution here is provided. Solution here is provided, okay. The inductance should be calculated as n phi divided by I, n phi divided by I. So that y n phi divided by I will give you this equation. So I will not talk about this in very detail because it's too complicated. I don't think it will be tested in the final examination. Okay, so to save your time, so that I will not talk about in detail. But if you want to look at the solution, my solution here is provided. Again, you have to do some integrations. But I say I think this is too difficult. But what I would like to comment on here is, okay, this question, you can say this is a solenoid, arranged in the circular shape. You can say its inductance only determined by the height h on the inner and the outer radii of this solenoid. You can say L is only a factor of the geometry and the number of turns. Okay, L only depends on H, A and B. H is height, A and B are inner and outer radii. N is the number of turns. Okay, it's only a factor of the geometry. Does not depend on the magnetic field or the current. Okay, it's only a geometry parameter. So that also another thing here is in the final examination, if when you read some question, you find, okay, some part is quite difficult, but do make sure you read through the question as a whole, because the second part asks you to compute the self-inductance of 500 terms on the ABH given here. So it actually asks you to just submit 500 A, B, and H value into this equation to get the final answer. So it's actually, which is very easy. So actually, although I think this question will not have a high chance to be tested in the final examination, but even if it was tested, I don't think the first part will take a high mark. Maybe the second part will take even more mark there. But do make sure you read through the last part. If you find, okay, the first part is very difficult and you give all the question out, that is, quite a waste of, so that's a pity. So what I would like you to suggest you is you go through every part. Because if one part is very difficult, the other part normally directly asks you to apply some certain formula. You can directly get the answer. So similar to this question, the first part asks you to get the inductance, that is very difficult. But in the second part directly asks you to substitute the geometry parameter back into the inductance so that you can get the final answer. Okay. So this is what I think this question is tested you. Okay. So just substitute, what is required in this equation, this torus, and then you can get the final answer. Okay. So then the last part about the inductor is, okay, what is inductor is used for? It can be used for us to store the magnetic energy. Okay, just like the capacitor can help us to store some charge, so that we can store some electric energy in the capacitor. Inductor, for example, if the inductor is made by superconductor, then when we inject current in it, the current will always be there. And also, if current is there, magnetic field will always be stored in the inductor. So there will be magnetic energy. And the amount of magnetic energy stored in the inductor is half Li squared. Half Li squared. This is similar to half CV squared for electric energy. Half Li squared is the magnetic energy. Okay, this is the last part. Okay, so the final chapter 5, is about electromagnetic wave. So for electromagnetic wave, I don't think, so of course it's very complex, but for our class, we only require you to understand or to apply 6 formulas. So first, so let me tell you what is magnetic wave. So we know changing magnetic field will generate EMF. So EMF is actually similar to electric field, right? Actually, changing electric field can also give rise to a magnetic field. So you can say changing electric and magnetic field are bound together. So they will, in this case, they will propagate in the space to create a wave called electromagnetic wave. So you just understand the electromagnetic wave as a time-varying field of electric and magnetic field. Time-varying field of electric and magnetic field. Then the first important thing here is the energy delivered by this electromagnetic wave. Energy delivered by this electromagnetic wave is given by E cross B. Okay. E cross B will give us the direction of energy flow. E cross B, and the magnitude of E cross B. Okay, the magnitude of E cross B will give us, the intensity per unit area. Okay, the intensity, also the power per unit area, which is the intensity. So the intensity is actually E cross B, E times B divided by mu naught. This is the power per unit area, which we also call the intensity. Okay, but this is time-dependent intensity, not the average intensity. The average intensity is actually the maximum S divided by 2. Because E and B are changing in time for electromagnetic. E and B are changing in time. Actually, okay. So the time average of this time-varying intensity is what we call the average intensity of the electromagnetic wave. So as I said, the intensity is power per unit area. This is E times B divided by mu naught, give us the power per unit area. Okay. E divided by B is the speed of the electromagnetic wave propagation. E divided by B. This is always equal to a constant C. So this is why Maxwell found that electromagnetic wave propagate at a speed of c. He quickly commented that light is actually not a particle or wave, it's actually electromagnetic wave. Okay, light is a kind of electromagnetic wave. It just falls in the visible spectrum range. But apart from light and the visible spectrum range, we also have the long wave and the radio wave. We now use for our wireless communication. We also have thermal radiation, X-ray and gamma rays. Okay, so these are all kind of electromagnetic wave in the spectrum. The visible light we see just occupy only a small portion of the whole electromagnetic spectrum. Okay, but the visible light, this sunlight, is a kind of electromagnetic wave. Okay, it's a kind of electromagnetic wave. Now I already told you two formulas. One is E divided by B equal to C, speed. Then E times B divided by mu naught give us the power per unit area. Okay, this E times B divided by mu naught times S is the total power. Okay, so these are two formulas. Then there are other 4 formulas. The first one is there are some electric energy stored in the electromagnetic wave. Okay, the electric energy stored is equal to half epsilon naught E squared. Magnetic energy stored is half B squared divided by mu naught. Both of them are equal to each other. You can show. So that the total energy equal to UE plus UV. So which is epsilon naught divided by E squared or mu naught divided by mu squared. So that the average, the average energy is given actually by the maximum B and maximum E divided by 2. Okay, divided by 2. These are the 4 important formulas about the energy. Both of these 4 formulas are provided in your formula sheet. So again, for electromagnetic wave, 6 important formula. The first one is C equal to E divided by B. C equal to E divided by B. And the EB divided by mu naught is the intensity, okay, or power per unit area. EB divided by mu naught is the power per unit area. And then another formula about the energy stored in the electromagnetic wave. So you can say, so once you know this 4 important formula, you can say all the questions about the electromagnetic wave are tested to apply these 6 formulas. 6 formulas. So for example, question 5 asks us to determine, okay, said, okay, here we have a 15 micron volt helium laser. It emits a beam of circular cross-section with a diameter of 2 millimeters. Want us to determine the maximum electric and magnetic field in the beam, maximum amplitude of the point power, maximum energy density of the electric and the magnetic field, and finally the total energy contained in 1 meter length of the beam. So as I said, what you have to bear in mind is actually the intensity. The intensity just equal to E squared divided by mu naught C divided by 2. Okay, this is the definition of the intensity. This is the definition of the intensity. Okay, the intensity, as I said, is a power per unit area. The power here is given 15 micron watt. 15 divided by its cross-section area will give us the intensity. So that you just equal the formula. So this guy is providing the formula to the intensity, okay? E squared divided by 2 mu naught C. And this is equal to the power per unit area, pi divided by R squared. P divided by S, this will not be given in your formula sheet, but you have to remember, okay? The meaning of intensity is power per unit area. Once you say the intensity, always use the power of the light source divided by S. And then let this P divided by S equal to the formula provided in your formula sheet. Okay? So once you do that, you can directly get what my E it is. As I said, when you get E divided by C will give you B. Okay, direct after the formula. Okay, the first formula, E divided by C equal to B. Then point power, as I said, is EB divided by mu naught. EB divided by mu naught. Okay, EB already given, so that you get this guy. As I said, the maximum point power is just twice of the intensity. Okay, maximum point power is just twice of the intensity. Okay, which is this guy. So for say electric energy half epsilon E squared, half epsilon E squared, also apply the formula. Magnetic energy B squared divided by mu naught, also direct apply the formula. So finally, the total energy E max, the total energy UE plus UV, twice of it. So that's one. Total average energy intensity just half, just 1/2 of the maximum energy. So divided by 2. So 1 meter beam, 1 meter of the beam, so that we use the energy density times the volume of 1 meter of the beam. So cross section is pi r squared. 1 meter of the beam times its height 1 meter. So that is the volume. This volume times the volume density of the energy, we can get, okay, this is about 50 picojoule. 50 picojoule. Okay. So normally for electromagnetic wave is repeatedly apply these 6 formulas. Okay, these 6 formulas. So the last question, okay. So the last question, okay, this is a question tested about 4 years ago. So here we have a laser beam with a diameter 3 millimeter. Okay, again, cross section is given because it's a diameter, so which means a circular cross section. So it has a maximum electric field given by this one. I want you to find the maximum value of the magnetic field, the maximum value of the point power, and then what is the wave intensity and output power of the laser beam. So first, the maximum value of the magnetic field apply which equation? B equal to E divided by C. Very good. So that's the first one is very easy. You know, apply the formula B E divided by B equal to C. So that my B should equal to E divided by C. So once B is given, the maximum point power can be calculated, which is E times B divided by mu naught. Okay. So apply the second formula. What is the definition of the point power? As I said, the wave intensity is just 1/2 of the point power. 1/2 of this point power. You can also apply this E squared divided by 2 mu naught C, or directly divided by this by 2. You can get, you know, the intensity. So once the intensity is given, how should I calculate the power? As I said, intensity times the area will give us the power. Because intensity power per unit area. This gives us a diameter because intensity I is power per unit area. So that my power is I times A. It's circular cross section. So I use pi r squared to get its S. So it tells us, okay, it's 3 millimeter diameter, okay, of this laser beam. So that its radius is 1.5 millimeter. Pi r squared is S, okay, is A. I times A will give us a total power of this laser beam, okay? So again, as I said, for electromagnetic wave, just repeatedly apply this 6 equal formula. One is E divided by B equal to C. The other is dB divided by mu naught equal to my point power. So the final one is, you know, the 6, you know, or 4 formulas for the energy intensity. Okay, for the energy intensity. Okay. So that this will be the end of the class. If you have any question, okay, I will still remain here to clear your doubts. So I think because we have some delays within the class because of the video. So if you have any question, I will still remain here to answer your question. Otherwise, the class can be dismissed. Yes.
Last question, why the C should be the speed, right?
Sorry?
The C should be the speed.
Yes, C is the speed.
But why the last question that the diameter is the 3 millimeter?
So what do you mean? Diameter and the...
E divided by B equals to CR. Then
D
we don't have speed here.
Sorry?
We do not have speed, we only have a diameter. Why we use the diameter instead of?
So this is not diameter, this is light speed. 3 times. Yeah, this is the speed of light. C is the speed of light. So this is not 3 millimeter. This is 3 times 10 to the 8 is the speed of light.
Oh, okay.
Okay?
What's the difference between pointing vector and intensity?
Very good. Point power is actually like, I would say similar to intensity. Intensity is the time average of the point. Because E and B are both changing with time.
Okay.
So my point power is also changing with time.
Okay.
But the intensity is not changing with time, which means I average the point power in one period. That is the intensity.
Oh.
So this is why intensity is always the maximum point power divided by two. Okay. Because a conveyor field is maximum, is always, you know, is max. So the average of a conveyor field is always a maximum field divided by two. Okay, intensity and the point power is the same thing. But the point power is high, so which means an area level, the power at given as the rule and the intensity delivered, you know, is a lot of that. But normally what we get is, for example, you recognize the measure the average intensity. So the average intensity is the average intensity.
Okay. So the pointing vector is like the instantaneous.
Yeah, the instantaneous.
Okay.
The instantaneous. But in this thing is average.
Okay.
Both of them has S.
Okay, good.
No problem. Yes.
First question, how do you get 4 pi from 2
No.
the R
R divided by 2 times 2. You have 4 pi R times R divided by 2 is 4 pi R 4 divided by 2 is 2.
what do you but then
Sorry.
oh
Because why I need to get this one? This is because I want to write.
you suck in the R here.
Yeah, because I want to write my R divided by 2 as 0.06 times sine theta.
Oh, so you expand
Yeah. Yeah, this is because this is my half R, right? 0.5 times R. 0.5 times R is this L times sine theta.
Oh, so overhead times 2 then.
Yeah, so why I can write 2 pi R as this 4 pi times 2 R is because 4 divided by 2 equal to 2.
Oh, okay.
Right?
Yeah.
Okay.
How do you determine the red color?
How do you know the using the right hand rule?
Because we use current to generate a magnetic field. We only use one right hand rule. For example, 3 right hand rule we learned last week. 2 is with regard to the force. The force is always 3 fingers. So if it's a moving charge, then it's QV, BF. If it's a line current, this is IBF. So this is related force. Only when magnetic forces are involved, we do this one. But if it's a current generated field, this one, this one. So this is current generated field. So we first apply this one to determine the field. The field is determined. We want to get the force. Right, is B on the force, magnetic field and magnetic force under this one. B, sorry, I, B, F. So
C is into or out?
yeah. So you can say this one. We have current generated the field, so that at this guy is into the page, right? At the left hand side out of, at the right hand side into the page. So once the magnetic field into the page, then we apply our right hand this way, because the current now flow into the bottom. My thumb point into the page and I get a repulsive force. So that the current should flow into the bottom. On the opposite direction, I get a repulsive force. Otherwise, if my current flow in the same direction up, I get an attractive force.
So the force is acting this way because it says I, so I think that
Yes. So only force involved, I apply 3 fingers.
Okay.
But if it's current generated field, I apply this. Okay, so this is what we learned last week. This week we have another right hand rules. 4 right hand rules in total. Okay. The first right hand rule we learned in today's class is this I nil cross B. V cross B give us the current flow in motional EMF. Yes, V cross B give us the current flow in this motional EMF. Okay, so that is for motional EMF. Different from previous right hand rules. But V cross B, VB give us the direction of the current flow in this motional EMF. And also this current flow also points to the higher potential end.
Okay. So now this one is the current.
Yeah, this is the current.
Motion.
Yeah, for motional EMF, this is the current. This is the V. Oh, sorry.
VBI.
VBI. Yes, VBI. This is for motional EMF.
Motional EMF.
VBI.
Okay.
The last one. So that you should remember this step. So previously about magnetic force and magnetic current, about magnetic field. The 2 right-hand rules about magnetic forces.
Oh, VBF, IBF.
Yes.
Now is
No, this is QV. QV, BF, IBF.
And now is
VBI.
So they got 3 different ones.
So to a 3
Sorry.
different
Or 3 different.
got this one also.
Yeah, 4. This is the
current.
current. Yeah, we got 4 right-hand rules.
Okay.
We got 4 right-hand rules. So as I said, last week's QV, BF, IBF, So to this one, B.
V.
Oh, so sorry. V,
B,
B,
I.
I.
Okay.
And then I, B. I, B. Okay, 4 in total. Okay. So that because the magnetic forces always reflex.
Okay.
And also this V, B, I also this reflex.
Okay.
Only I have I and B. I generate B. Use this one.
Okay.
Okay.
But so in this question, right, the two rod, right?
The two rod.
So
first.
the first step you have to identify the magnetic
Yes, you
field,
have to
right?
calculate magnetic field. If no field, how can you get that force?
So let's say if I want to analyze now for example on the big one, this one. Let's say I want to analyze now wire 1. Where's the force acting on wire 1? Do I have to find the B field of wire 2?
Yes,
So
of
it's like that.
course, of course.
So that's out of the page.
Yeah, so if you want to have B field on wire 1, and then so also into the page, it's in this way. In this way, so on the right hand side out of the page, on the left hand side still into the page. So right, so it's into the page. If it's into the page, and then you apply this the right hand rules I because I flow to the bottom, B into the page, left to the left, repulsive. Okay.
So the force of the wire is always affected by the B field of the
Yes.
opposite wire.
Yes, the force always was affected by the field of the other wire.
Oh, okay, yeah.
So you need to determine what's the field.
Field. If you low
Based
field,
on the
there is no
current,
force.
whether
Yeah.
it's
Yes. That's right. You first to have to determine the field, direction of the field.
Yeah, this one.
For the second question, the square one.
Actually, ask me go through
How do
example.
you know like? How do you know that the D got no force here?
Because B is not in the field.
So it's not in the field.
Yeah, it's not in the field, then you don't have B. If you don't B, how can you get that field? Or how can you get that force?
Actually, I don't know how to use a formula. Formula about a lot of things. Like, how do you determine which formulas to use for which situation?
Which formula to use for which situation? Then you have to remember this one. Yes, you have to memorize. You have to memorize because we don't want you to memorize the formula, but you have to memorize the concept.
Yeah.
So normally, if you have the loop moving into magnetic field, that is BIL.
Oh.
You have to remember this situation.
Yeah,
This is what you have to memorize.
Because I want to learn how to link the formulas together.
Yeah. This is what you have to memorize the way.
Yeah, correct. Okay.
So you attempt many
So
questions.
keep doing.
And keep doing it,
Okay.
and then you can get such a feeling and such memorize.
The wave one's okay. The wave one just a full formula. This one is this one is the one that he just explained. The two wire again. Yeah. This one.
What's this?
The exam question.
So this is the second question I talk about. The what's your question?
No, this is.
Yeah, this one.
This one.
Oh, okay.
So on the same direction.
Oh, same again, right?
Yes.
Okay. Oh, then should be okay.
Can I ask, right, for this one, right, the last part, when they ask for total energy contained, right, why do you use the average and not the total energy that I found here? Why use average times the area?
Oh, yeah, of course, because the total energy is changing with time. When you get for example, if it asks you to calculate the power or asks you to calculate the total energy, always use the average. For example, the power is the intensity. Intensity is the average point of power. Intensity I is the average point of power. So if you want to calculate the energy, you of course need to use the average energy density, not the total energy density.
So like the first part when they say when they ask for the intensity, so I just multiply the average of it.
Yeah. The intensity is the average of
So
it.
it's always
Yeah.
average.
So this is what we use this one.
That's
Yes.
why I use the
The
average of
intensity
that.
and the power, if you refer to the power and energy, always the average.
Use the average.
Average, yes. You just remember that. The total energy actually is changing with time. It's changing with time if the right because E and B. So this is actually the total maximum energy intensity. So only at a certain instantaneous time, at a certain instantaneous time, you can get this guy. The other it will vary from 0 to this value. So of course when you calculate the total energy density or the total energy, you cannot use a maximum. You must use an average. Okay. So what I would like to say this way, the maximum does not have any physical meaning, because the maximum, for example, point power or the maximum this total energy is not what you can measure. What we can measure in our experiment is always average.
Okay, so
Either
I just
intensity or
always use average.
the average one, yes, to do the calculation. If you want to calculate the power of the energy, always use the average one. Yes.
So just now you say that you got upload like
Yes,
the
your
thing,
content.
right? So is it content?
Content. Yeah, this one. Yeah. From week 1 to week 5 to week 7. So there are many how to say the.
It's different from the one that you sent in the MS Team, or is it the same?
I don't send anything on MS Team.
MS Team, the PowerPoint.
The PowerPoint is our tutorial.
Oh, so it's
So
different.
there's a different.
Okay, that's
Yeah, so that is normally because in the past I talk about the electromagnetic simulation, so that I will include some question there that is help student to so help you to do quiz tour. But now I don't think they put so many questions because I think they can give more examples, but not just preparing for quiz tour. So my way is okay. I think physics is a lot. You just need to understand some example. You need to try to do some, for example, questions in order to strengthen your understanding about certain formula. So that in the past I will include many questions, more additional questions for the student to try. But now I think the other lecture changes the way of doing that. But anyway, I think my question there will still help you to prepare questions. If you want to, for example, have time, you can go through there. This is all exactly, question from question. It's not a sample question. Sample question is they give you as a sample, but that they take from the database. So the sample question will not be tested. But what I tested here, I just change the value. All the questions are directly from question.
like the back of all.
Yes, it's all exactly question. Just I change the value. I change the value. But the question is there in the database. The sample question is not the question in the database. Once they use the sample question, which means they take all the square question, yes, from the database. But what I put there is the question that may be tested.
Yeah, I'll try.
Okay, good. Yeah, no problem. Yes, any question?
No question.
As I said, I have some. So if you want to, I think my question here is even more useful than the sample question. Sample question is, testing tells you how it looks like. But once you put there as sample question, they will take that from the database. Sample question will not be tested. But what I put here, for example, such kind of question, what I put here, so here I have some, background. But what I put here, for example, like this one is exact the quiz to question, so it's still in the database. So and also this one is also in the database.
Very good.
Also in the database, maybe I change maybe it will change a little bit the value, but all the questions are still there. For example, this one, all the questions are directly from the question here. Maybe it will change the value a little bit, but all the questions are here. So you just because I prepare for the. So actually, because I prepare for the second part. Only I prepare for the second part. Now they change the lecture because some other young professor they need to promotion. Promotion they need a bigger class. They ask me whether I can give my role to the other young professor to teach. But I am still preparing the content here. So that this is the content I put there. So all the questions is what I put up on Facebook.
So just study this.
Not just, I say 600 questions.
600 questions.
600 questions in database, you will be randomly tested 6 in the database. So different one will have different questions. But what I put here is normally the student.
Repetitive.
Then first, this question are very typical. And at least what I told, for example, at least more than 40% of the student getting the one, I will talk about it. The other I didn't talk about normally very easy question, direct and concept. But here I think some students easily get wrong. I will just put up here. So that it also contains, as many, for example, concept to help you to do the revision. Okay, so you take a look at this will be, I would say if you want to prefer a quiz tool, I think this one is much more useful than the sample question. That's much more useful than the sample question. Okay.
Maybe Prof, if you have any question with regarding revision or with tutorial, can I email you and?
Yeah, of course. Okay. You email me or you contact me as I said, every Friday afternoon at the consultation session.
Can.
You can either, for example, if you want to consult online, you just make a appointment with me and I can, for example, to block my calendar. Or you just directly, if you are in the university, directly come to my office.
Okay.
You can consult face to face.
Yeah,
every Friday afternoon.
Okay, thank you, Prof.
Yeah, I told you every class that I will have a Friday consultation session every afternoon.
Okay.
But you guys still don't come. Okay, Friday afternoon. Or but if you don't want to continue with okay, we can also talk online. So I think online is even easier because we can share screen, right? I can share screen from my side. You can also share screen from your side. I think the discussion is also easy. But in this case, you have to fix the account for me to come online. Otherwise, I will just sit online, in my office. If you want to just talk to me online individually, you send me, for example, an email one day, maybe a month. For example, tomorrow evening or Friday morning. So that we can fix a time and to discuss online. Or you can just directly come to my office. Okay?
Thank you, bro.
Okay, no problem. Bye-bye. Okay, so if you request, maybe I will leave here.
The step response is 0,
This is the error.
the step response is some
No, I don't think so. At least I don't because some of receive an email from the higher, for example, from the school. This are to change. If the university must also require something to change because all original so you are paying online. So you need to benefit from so question one is because you are other subject on the month. We say to go to they are 2 years or something. Because the class is 6 so it's very difficult for us to have such a big dimension all the students. So now it's online. But if there is any change, the university change, you just look at this until the announcement, or we will let you know. But we will announcement the university. So if you have any question, email me or come to me on Friday afternoon. Okay. Bye-bye. No problem. Bye-bye.
Okay, submit